Thanks everyone for coming. This is a deep dive on Jaeger. If you had a chance to go yesterday for the intro, we hope that people sort of know what Jaeger is on a high level and the very basic functionality. So today we're just going to talk about new features in more details. And so I'll say a few words about the project status. We'll show new features and talk about the roadmap in a bit more details and maybe leave more time for Q&A. I'm Yuri Shkuro. I'm from Uber, working on Jaeger. Over here, Pavol is from Red Hat, also a maintainer. And Joe is also from Uber. He actually one of the authors of the new trace diffs that we'll be showing. So he was not originally on the list. So again, this is probably a repeat for many people. Jaeger is a distributed tracing platform inspired by the Dapper and sort of compatible on a conceptual model level with Dapper and OpenZipkin. And it's been a part of CNCF since last year. So we've had a good growth. We're actually applying for graduation now because we have like sufficient number of users and maturity of the project, and as well as like number of contributors. This is my pitch kind of from yesterday, is that I now think of tracing of Jaeger as not just a tracing system, but a tracing platform, which means that it's not just the thing that does everything for you, but it provides a platform to do more exploration, right? And so the main thing about distributed tracing as a tool set is that it's ultimately a root cause analysis tool. So when we have a performance problem in application, that performance problem can manifest as like some error rates thrown somewhere, or it could be latency. But in the end, it affects in some way the end user of the application, right? And so we want to find out where that problem is. And of all the existing sort of distributed monitoring tools today, distributed tracing is the best position to actually answer these questions, because it understands the flow of the application much better than any other tool. And as a platform, once you start collecting this data, what you really want to be able to do is like ask questions and prove, or like make hypotheses and prove them with the data that you're collecting. And without being a platform, it's like we can't really scale the project by building to very specific use cases that people have, like saying, oh, well, trace diff, we will show that this is something that we thought would be useful and we built it. But there are many other things that might be useful, but they may be narrow use cases. So by focusing more to be a platform where you can like do ad-hoc experimentation, I think we open up a bit more to people to use the whole like rich data that we're collecting. Technology stack is, again, the main thing, I guess, on the slide is the client library support. We have support for officially for 7 languages, plus there are 2 unofficial like community supported libraries. So we're pretty well covered if you have an application in production today that you will be able to instrument it for tracing, right? And on the backend, this is like a deep dive I will mention. So we have official support for Elasticsearch and Cassandra as a storage backends. Doesn't mean that you have to use them, but there people around in the community are trying to use with other storage backends. Right now, it sort of requires a fork of the code to build a different storage plugin. So we'll talk later about the plugin framework that we are kind of moving forward, where you would be able to, as an end user, you should be able to take Jaeger core and take a plugin that someone developed and just combine them at runtime rather than forking the code. This is sort of like not so much a project problem, but the Go language problem, because Go doesn't support plugins that well. And as a health of the project, so as I mentioned, we have 7 maintainers, like core maintainers from Red Hat and Uber, and we have like a lot of contributions from the open source, like 220 unique authors of different commits. So now I'll give to Pavol to show you some of the new features in a live demo.
So hi, I will show you actually one feature. It will be introduced in the latest release, which is 1.9. So I will just generate some data. So this is the basically main screen where you can find all the traces. And this is the trace like timeline diagram, which shows you the structure of the call graph. And we have introduced this new trace graph, which helps you to understand like large traces with a lot of spans. And what it does, basically, it groups spans from the same service with the same operation name. So for example, here we can see that this one is interesting. It's from service driver. We can see that it's grouping spans with the operation driver find nearest. This is not a very good example because there is only one span representing this operation. But if I go, for example, here to the road service, we can see that that front end called road 10 times with this operation. What is also interesting, we can see like the total duration. So it's the sum of durations of all these operations, and also the so-called self-time, which tells you like time spent within this operation minus all the like child of operations. In this case, there is no child operation, so the durations basically equals. We have also this toggle. If I switch it, it will change colors. And the idea is that it should highlight the nodes which are taking the most time within the trace. I think this is still prototype. It's not yet in the master. So we will maybe change some color schemes. Huh? Trace diff. Doing this one? Yeah. So what I showed you is it's useful to understand the structure, but also to compare the durations. And what we also have is the trace diff, which focuses only on the structure of the trace. So you don't see durations, but you see only differences between like number of spans between these two traces. So in this particular example, we are comparing A and to B, right? And this is red, which means that B trace doesn't contain one operation from the Redis service. Yeah, if it's like, it can be also in green, it would mean that there is one more span from the Redis. I think Joe will talk more about this trace diff with more like, this is a very simple example, but if you have a lot of spans, it helps you to understand when to focus. So what we have also new is the new website. And the nice feature is this client features comparison. So you can see like what clients support, like what kind of protocols, what kind of senders. And also there is a page where you can find all the components, like the agent collector, the Jaeger collector, Jaeger query, Jaeger agent. Yeah, and the download page, which is basically the previous. Okay, Joe, do you want to? Yeah.
Hello? Okay, great. Hi, I'm Joe Farrow. I work on Jaeger, primarily on the UI. Great to be here. So let's talk a little bit more about trace diffs. Okay, this is the first time I'm seeing this slide. The Gantt chart is great for traces with, is not great for traces with 10,000s of spans because they just get kind of overwhelmingly complex. It's too much information. So with trace diffs, you do two things. One, you compare two traces, and also we also compress or condense or reduce rather the graph that represents the trace with the counting, where you can have one node that represents multiple spans. Additionally, we've done some research on comparing one trace against a group of traces, which has proved pretty interesting. People are showing some affinity for that. So that's something we're actively exploring for a future release. So the trace graph, which Pavol mentioned, is a single way to kind of reduce the complexity of a trace. So, okay, so here's a trace diff. Pavol went into that compression, that reduction, so I'm just going to go through a little bit more about the coloring and kind of the way this works, and also talk about this as a scenario. So down here we have the root node. The root node's gray because that node exists in both trace, and it's also has the same count. So there's one root node in both traces. Down here we have dark. Oh, by the way, these colors are modified, so they have more contrast in the screen. They actually don't quite look like this. I can't see it, but yeah, so FYI. The colors are adjusted to kind of like have the differences more apparent. So down here we have dark red and dark green. That means this node is in one trace but not the other. So if it's dark red, it's in trace A but not in trace B. If it's dark green, it's only in trace B. Up here we have light red and light green. So that means it's in both traces, but there's more spans in one of them. So for instance, if it's light green, then it's in both traces, but there's more of those spans in trace B. Okay, so if we look at this trace, we try to kind of create a narrative about it. We have this section in the upper half that's gray, which means it has a lot in common structurally. And then we have some differences over by the 3, which means things start to diverge. And then around the 2, we have major divergence. So we kind of have two things that are going along similar paths with some differences, and then they basically fork. So the rationale, or the story behind this, is these are two eats orders that are both post requests, so to create an eats order, and things are kind of going along on same paths. And then when the user's credit is checked, the user in trace B doesn't have sufficient funds, so a rollback is issued, whereas in trace A it continues and finishes the order. So the dark green nodes are actually the rollback nodes, and the red nodes are the finalizing of the order. So if we didn't know that, for instance, we can just see that there's very strong divergence later in this trace. We can go to the trace timeline. Now, this is a section that has the divergence. We can go to the trace timeline, and we can see an error message that says you have an outstanding balance. So that's kind of, we can either start from there and find a trace that has a finished order and then compare them to kind of verify our processing, or we can see that there's some divergence in this and then drill down to get the rationale behind it. Another form of comparison is understanding the duration of the trace. So if we look at this trace comparison relative to the previous one, we can see it's much similar. There's far fewer differences between A and B. So here we have a lot of gray nodes, and we have some green nodes kind of in the sort of lower half of it, some red stuff in the upper half, but basically it's very similar. And these two traces have similar number of spans. A has 507, B has 526, but they're actually very different in terms of their duration. Trace A has takes 2.74 seconds. Trace B is a 50% increase in duration. So it's a pretty massive increase, and we may care about that. So we can kind of try to reason about what might be attributing to that. I think there's three kind of general theories before we dive into actually understanding it. The first is maybe it's this difference. This green area may be slow, and we can maybe attribute the duration increase to this area, which is only in B. Or another option is maybe we can think like, okay, maybe like it's kind of spread out. B is just generally slower. The time is sort of distributed amongst it. And the third option would be it's something else. Turns out it's something else. So this view is coming soon. It's not currently in master, but with this view, we modify the coloring of our nodes to be based on the duration of spans in those nodes. So we compare for any given node that's shared between the two traces, we compare the average duration of the spans in A versus the average duration of the spans in B, and then we color them. The darkness of the colors is based on the maximum difference for any given node. So we can look at this and we can see, okay, so over here it's all gray. That's because they're very similar in duration. And then over here they're white. This is a section that's only in trace A, or trace B rather. So if the nodes are not in both, then we don't have a basis for comparison. So we don't actually color them. We leave them white to indicate that there's no common ground there. So here we have the root node, which is dark red. It maybe just kind of looks like dark gray in the screen. That's how I increase the contrast for the projection. So it's dark red, and that's natural because trace B took 50% longer. Now, if we follow that, we can see that of the children of that node, only one is dark red. So that means the duration increase is concentrated into that child. And if we look at that child, we can see it has one dark red node and kind of two more sort of reddish nodes. So we can conclude that the duration increase is actually highly concentrated in this trace. So if we mouse over this node, we can see wizardly omega accounts for over 1 second of increase in duration, and the node below it is 200 milliseconds of increase in duration. So with this, we can kind of dispel our sort of speculation and see that the duration increase is highly concentrated. And I think that's all I have. Yeah. Thank you. Oh yeah, sure. The graph visualizations. There's that condensation of the structure, the reduction, so that facilitates like dealing with like we have traces that are sometimes like 80,000, but then they have a graph like in this view that's similar to the hot rod demo more so than the eats post. So it kind of highlights how much repetition there is in sometimes supermassive traces. Additionally, there's presently no way to drill down into details. So one benefit of that is you're not overwhelmed by those details. And then yeah, those are the main differences. And we also color code and highlight the structural differences. So and we emphasize the structural and duration differences to kind of call that out, so you don't have to. One of the challenges of using the timeline view or even the trace graph view in isolation is if you want to understand the distinction between that graph, that trace, and another one, you kind of have to piece it together in your mind. It's a lot of cognitive overhead. So with this, it kind of highlights those differences. And then additionally, currently, there's distinct comparison modes between structural differences and the duration differences. And so that kind of compartmentalizes that sort of analysis. In future iterations, we may visit combining some of those and also creating new forms of analysis, like maybe comparing self-time or something else. But in that process, one of the challenges is going to be to keep the UI approachable. So, thank you.
Test. So one thing I want to add about trace diffs is that what's interesting to me is that I think there are like two fairly distinct use cases that people are applying distributed tracing to, and it kind of reflects in the complexity of the architecture that people have in their systems, right? And so the classic use case of the trace, this is something that like Pavol originally showed. Oh, you have a hot rod trace, you have maybe like 5, 6 services. You can reason very well about that architecture from one single trace. You can investigate it. And that works well to like a certain number of services in architecture, maybe, I don't know, up to 50. And at some point, you tip the scale to the architecture, which is as large as Uber, where we have 3,000 microservices. And suddenly, that same analysis becomes no longer as easy, even with distributed tracing, because as Joe mentioned, the cognitive overhead of actually trying to understand when you're looking at a trace which contains like 80,000 spans is almost impossible, right? And so surely you can like drill down into very specific parts of it, saying, oh, I know that this service is having a latency, and you can look into. So if you zoom in into that trace, then that actually still makes sense, right? But if you're trying to comprehend overall picture, or even trying to understand, well, I know that this trace represents some sort of failure scenario, but how do I root cause it? That's where it starts to break down, the classic tracing approach. And so that's why we went into this more sort of aggregation approach, where we say, well, we can try to do some machine understanding first, and then basically facilitate for the human to pinpoint where we think there might be problems. And so like, visualization is obviously one of the easiest ways to do that, because like we give signals to the visual cortex of the brain, which is a very powerful machine to actually try to see the patterns in it. Now, as far as the other features, I think quick call out to a bunch of integrations that have happened over the past year. Recently, the Jaeger operator was released for Kubernetes, which allows, like we used to have a Helm chart. I think operator is like a lot easier to use for actually just deploying to production. Then OpenCensus is another project which is sort of working on the instrumentation side of the things, and it has full support for Jaeger to export data into Jaeger. Istio, the service mesh, mesh, which is like mostly for Kubernetes. With Envoy, if you run Istio demo downloaded, then it comes up with Jaeger by default, and so you can get traces from any Istio demo application that you use. And obviously in production, you can also configure to spin up Jaeger and integrate with it. And because Istio by default uses Envoy, we've recently had some work done on a C++ client for Jaeger. So not only you can integrate Jaeger into C++ applications, but also because Envoy is written in C++, now Envoy can use the actual native Jaeger client, which allows the same flexibility of, for example, adaptive sampling and other things that we've had built into our clients, like the feedback loop back into the client. So that can be done inside Envoy. Before it was like very high-level integration only. And finally, this is not something that I use. Pavol told me about. This is the Eclipse Trace Compass. So it's a project in Eclipse incubation, which allows you like importing and visualizing traces as well. So another thing which was kind of a major change since last year is we went into a different architecture for Jaeger ingestion, at least internally at Uber, and it's like open sourced. So the original architecture, which when we just first open sourced it, looked like this. So in your application, you have client library, Jaeger client, which collects the spans and sends them out to the agent running on the host or in the pod or as a sidecar. And then agent pushes that data into Jaeger collectors, usually a cluster, and those push data into some like distributed database, right? Cassandra, Elastic, or whichever other database you want to use. So that was sort of like designed around the push method, and collectors and agents and clients, they all had load shading capabilities so that they had the internal buffer. So if they can't send data fast enough, they'll just drop the data, right? So all those things still exist. But what we've noticed in our experience at Uber is that when we have some traffic spikes, maybe there could be different reasons. It may be like Halloween is like the biggest day for Uber for whatever reason, I don't understand. But like it's like highest traffic over the year always, right? And so if we are like under provision for whatever reasons, that traffic may sort of overload our database ability to actually ingest all the data in a push manner in real time. And as a result, collectors, even though they have like internal buffer, that buffer fills very quickly if the database is not fast enough, and so you just have to drop data. And the worst part about it is that you have to drop data completely indiscriminately because collectors receive spans from like hundreds of hosts. Like you only know about what a trace is after you stitch it from the database, right? And so collectors make these decisions about dropping spans completely randomly because they have no context. I was like, oh, it would be nice if they say, okay, well, let's just shed 10% of the traffic, but consistently so that we can still keep traces. But that's physically impossible because of the stateless nature of collectors, right? And so I guess this is like a summary of what I'm saying is like the push model was struggling with traffic spikes. And there are multiple reasons for traffic spikes. It could be like a real business traffic, or it could be someone deployed an application with 100% sampling by mistake, right? And suddenly floods our data, the pipeline. So the data drop was always like unacceptable for us. We wanted to get around that. And so we've looked at Kafka. Kafka at Uber is like well maintained. There's like a team running it. It's a super huge cluster. It's doing like terabytes or like trillions of messages per day or something like that. So it's very elastic as far as the volume of tracing data that we put in. Like it's comparative to the overall cluster, Kafka cluster is nothing, right? And so if we have a traffic spike, the Kafka cluster can easily take like 10 times or something. And so it's very elastic, so it allowed us to not lose any data. We still have a push. So this is the kind of the new architecture. We still have a push between agents, clients into the collectors, but then collectors only write to Kafka, and then they're done. And so there's no data loss almost ever at this point, unless there's some like Kafka maybe brokers having a bad day. And then we released two new services called Jaeger Ingester and Jaeger Indexer, which read the Kafka stream and they like actually store the data into the database. And the reason we separated them is because, again, there is different value of storing the spans themselves which is very valuable. It's a raw data, and then building indices so that you can search for those spans. Like indices are like less important, and so we actually split them into separate Kafka streams so that like if we have any capacity issues, temporarily we can just shut down that ingestion, but keep ingesting all the spans into the database. And the second big reason why we went into the Kafka approach is that, as I mentioned at the beginning, we wanted to develop Jaeger to be more of an exploratory platform. And we internally use Flink streaming, which kind of works well with Kafka. So having all the spans available in the Kafka stream allows us to start building a lot of big data jobs on top of it in a streaming fashion, right? We also happen to have an infrastructure at Uber where any Kafka stream can be just flushed to a ZFS, which is also useful. We can get all the spans, historical spans in ZFS with like much longer retention than what we have in Cassandra. So this was the main reason, and yeah, it's all in production now. And in release 1.8, it's available for use. And there's also a kind of an interesting moment is that there was a ticket in Jaeger back in 2017, someone asking like, oh, can we have Kafka? And I said, no, we can't. But what people were asking, they were asking to have Kafka between Jaeger client and collectors, right? This is something that, for example, Zipkin does. Their clients can actually write to Kafka directly from the application, right? And we still think this is the wrong way. One reason is because it actually introduces a lot of dependencies on the application. You kind of get into dependency hell with like having Kafka driver inside your application if you don't need the dependency. Our dependency is UDP. That's it. Like every language has a UDP in it. But the more important thing is that all the feedback loop, that the red lines in architecture, they become very hard if you actually have like a Kafka where you have to capture everything, right? And so, so basically, we have Kafka after the collectors, but up to the collectors is still push mechanism. We have no plans to change that. Another big change, which is sort of like more internal, but the reason it might affect users in the end. So we've done some work to convert internal data model to be protobuf driven. So we have an IDL which kind of drives the internal domain model, and then all the communications between components inside Jaeger backend happen with that domain model, right? And what that allows us in the future, it unblocked several PRs that have been long outstanding. One is we can finally define a clear API for the query service. So today, query service does have an API, but we intentionally didn't document it because it's like some manually constructed JSON. We didn't want to be forced to stick to that one. And so with the IDL in protobuf, we can actually have very clear documentation about what the JSON API is. And similarly, the storage plugins that I mentioned, the Go doesn't have a good support for plugins like Java has, where you can just drop a jar. So in Go, you have to, one approach is like a HashiCorp plugin, which does the gRPC between two processes as a way of plugging new functionality, right? Kind of a sidecar approach. And so this is the one that we're experimenting, like there's a pull request in progress. And again, having gRPC and protobuf model as the kind of core foundation inside the Jaeger enables this much easier. And finally, people have some problems with the fact that our agents to collector communication was over proprietary Uber protocol called T-channel. So sometimes it's hard to route because routing may not understand that specific protocol. But so we switched already to gRPC. It's going to come out in the next release as an official. And then I think in the next release, we'll just make it a default. So we will deco the T-channel path so that it's a lot easier to route. I guess I have all these things that I just talked about. And finally, like Zipkin compatibility has been improved since last year. So we have compatibility now on multiple levels. So collector can accept Zipkin data. So if you have an application instrumented with Zipkin libraries like Brave in Java and like in Spring, then you can just point it to Jaeger collector and it will take Zipkin data and process it as native data, right? Or alternatively, if you have a new application that you want to instrument with open tracing and Jaeger, but an old application instrumented with Zipkin, you can configure your Jaeger client libraries to use the same propagation format so that the traces don't get broken as they travel different types of applications, right? Yes, and we support like several actual formats that Zipkin has, like JSON, V2, and Thrift. And the only thing we don't do is we don't we are not able to take Zipkin spans from the Kafka stream, but we have all the infrastructure in place. Like if someone needs to do that, it's probably like a couple days of worth of work if anyone wants to put the PR for that. And finally, so I'm kind of like 2 minutes left. So I don't know, I will probably skip the roadmap. We will put the slides on the thing. So this is, I talked about most of this already yesterday. So I think the data pipeline is kind of probably the most interesting one. Again, is as our direction to take Jaeger to be a platform for data analysis. The data pipeline means that the Flink jobs that we have internally at Uber, Apache Flink, it's a streaming platform, we're going to open source them so that they will build a foundation of like, you can take like a library essentially to Flink saying, okay, in this library, if you run it in your Flink job, it will give you a view of a trace assembled from the Kafka stream. And after that, you can do whatever you want with that trace. You can like extract various features and do any analysis. And but we also like, we have big plans in terms of like how we can proceed on that data pipeline thing. Yes, and storage plugins, like I said, there's going to be this is ongoing work, and once the plugin framework lands in master, then I think people will start actually putting up new storage because we've had lots of interest, like ScyllaDB, DynamoDB, and all kinds of like cloud provider databases could be used with Jaeger as a plugins. And this I'll skip. This is less interesting. So website, as Pavol mentioned, has a lot of documentation on how to run things. This is our sort of social media stuff and ways to get in touch. And oh yeah, so this is the wrong slide. This is today. And I guess we only have a couple questions, but we will be around outside if you have any questions. So, but now I think I'm out of time, pretty much. Okay.